Good afternoon. Today we are going to have an art class. Yes, an art class. We want to learn how to draw. Q, E, and V. I think this is a very important skill that Faraday taught us about doing electric field lines. Along with the idea of electric potential, this is a very important skill for us to learn. So that's what we are going to be working at today. All right, so I'm going to be making use of the PHET simulation to help us to do it. What we're going to be doing is a number of charge distributions and try to do the electric field lines as well as the equipotential surfaces. So let's quickly review a few of the key concepts. First of all, for electric field lines. Electric field lines, first of all, they start at a positive charge. You can see here there's our positive charge here. They start at a positive charge. They will always end at a negative charge. Okay, they don't just disappear. They end at a negative charge. So somewhere there should be a negative charge to balance this positive charge somewhere in the universe. Okay, they will end at a negative charge. Now the separation between the lines reflect the strength of the field. So where these lines are closer together near the charge, that means the field is much stronger. Where these electric field lines are farther apart, that means the field is much weaker. Finally, note that when we draw electric field lines, they must have arrows to show direction. Okay, that's our electric field lines. The second thing we want to draw is equipotential surfaces. That would be 3D, or we're going to be just doing it in 2D, so we'll call them equipotential lines. But really they are surfaces in 3 dimensions because we're in a 3-dimensional world. So the electric field are lines. The electric equipotential surfaces are surfaces. Okay. So, but we can only draw a 2D cross section. Okay. So these are where V is constant. So the crucial thing about these equipotential surfaces, they don't have any direction. They are always perpendicular to the electric field. The potential at infinity is going to be, for our exercise, set to be 0 at infinity. In other words, the value of the potential at infinity is going to be 0. So the closer these surfaces are together, the more rapid the change in voltage and the higher value of electric field. So you can see they're very close together here, so it means the voltage is changing rapidly and the electric field is very strong here as well. Okay. Now, in order to learn how to do this, we're going to make use of the PHET simulation. So for each of the cases that we're doing, when you're trying to work through one of these cases on your phone, okay, you'll be using your phone to do a lot of work. I'll work through a couple of examples, then we'll pause, give you some time to work through them on your phone, using your phone and writing them down on a sheet of paper, the results, and then we'll continue that on. So in the end, you'll hand in the paper. So in using the simulation, first of all, place charges on the screen to try to simulate that sort of a thing, that sort of charge distribution. So for example, for this line charge, you'd put a line of negative charges on the screen. For our battery, we try to simulate this with charges on the screen too. Okay. We can then observe the E field vectors. We can use the tool to draw the equipotential lines, but separation between the equipotential lines should be the same delta V each time. And on your paper, you're going to write the value of the potential on each line. You can then also add sensors, a positive chest charge, to show where the electric field line is, and then you are going to draw the electric fields. Okay? So that's the simulation, how we're going to be using it. All right, so let's start with a few basic examples to show how we're going to use the simulation. You've done a little bit of this in the PBL, but we want to go more deeper now. Okay? Basically, we have 3 sets of examples to complete. Basic single charges. In other words, a positive charge, a negative charge. A dipole, a positive and a negative charge. 2 negative charges. A triangle of negative charges, that would be a negative ion trap. Or a triangle of positive charges, that's a positive ion trap. We'll then look at lines of charges a line of charge plus a single negative charge, and a line of charge plus a single positive charge. And then finally, we'll look at a battery with a wire, a battery with an antenna with a broken circuit, and a battery and antenna with a complete circuit. And if you want, you can also do a battery with an antenna, with a capacitor, sorry. Okay, and there's a handout. You will be filling it in. So using the simulation as aid, you'll be completing the electric field, and you'll hand in the beginning of the next class. If you could not finish today, you can work on it more at home, okay, to try to complete these examples. All right. Students, I think this is very important for you to learn to do, and this is a must-see. If you are not able to draw these electric field lines and these potential surfaces, you will not pass this course, okay? So this is definitely a must-see. Okay, now, okay, I'm going to start working, showing you how we can do this with the simulation, okay? Let's go to potentials and fields. Okay, here's our simulation. All right. Let's first of all do a single positive charge. Okay, and we can, okay, from the signal positive charge, you can see from the PHET, the direction of the electric field is pointing away from the positive charge, and the farther away we get from the positive charge, the weaker the electric field gets. All right, let's turn off the electric field now, and we're going to work on the voltage. Okay, you can see how it's brighter and it drops away. Okay, that gives us a feel for how it is. Now, if we want to get a little bit more detail, we can start with equipotential lines to see how the voltage is. This is where I'd like to start working with this. Okay, now, let's quickly view. So far away, we've got about 2 volts. Close by, we're up to about 50 volts. Okay, why don't we first of all put equipotential lines at a constant step of, say 5 volts. Okay, so I'm going to put first one at 50 volts. Actually 10 volts first. Okay, well, next one we'll do at 40 volts. Next one we'll do at 30 volts. Next one we'll do at 20 volts. Next one we'll do at 10 volts. Okay, so that gives us a quick idea. Let's maybe do another one way down around 1 volt or something. That's sort of hard. Okay, maybe we can do it at, put an extra line at 2.5 volts, okay? All right, so now, if I'm going to do this, I will now want to label each of these things. So this gives me an exponential line. So I want to label this as a 2.5 volts, etc. all the way up. Okay, let's turn off the voltage thing. So now we've got our equipotential lines. Now let's start to look at the sensors. We can put on the sensors here to get an idea what the electric field is like. Okay, let's put the electric field here, and let's turn on the values. Okay, so we, at this point, okay, we now have the values of all the different potentials. We also have an electric field here, so we can move this electric field along. We see that at all points it's perpendicular. It's got a value of 0.69 at this point. Let's put another sensor where it's 9.9 volts. Okay, all right, let's move this thing so it's always, again, pointing away from the positive charge. Let's stick it over here. So it's about 10 volts per meter here. Moving closer. 45 volts per meter at this point, at the 20 volt level. Let's move it closer, again perpendicular at all points. 101 volts per meter electric field here. Let's try to get closer. 178 volts per meter. And at the very closest one, well, I can't even see that now. Okay, 314 volts per meter. Okay, now I've got these basic ideas here. I'm going to want to try to now write some of this. I'm going to try to then draw this on my piece of paper. Okay? That will be my next step, will be to draw on the piece of paper. Okay, let's get started again. I'm going to now try to, for the negative charge, let's first of all do the, look at the voltage again, what it looks like. Okay, the negative charge is showing how the value is sort of the blue. They're representing negative with blue here. Okay, that's fair enough, but let's quickly use this guy. Again, we're going to do the same thing as we did before. 30, 20, 10, and then you can see it's dropping not very fast out here, 2.5, 40. Okay, so that's probably enough equipotential lines to give us the idea. We can show the value on them, and we'll then be copying this into the thing. Now, electric field, we can put a few sensors here to see how the electric field is. Okay, very little here, electric field 0.7. Electric field is much stronger here, pointing towards the center at 11.6. As we move toward closer to the center, 45. Closer to the center, 102. And at the final line where we had the 40, 227 volts per meter. So given these few electric field lines, few electric field vectors, we can now work on drawing the electric field lines. So I'm just going to redo this guy that we had just now. So if these are now electric field lines, that's a negative charge, it's going to look very similar to the positive charge, except for the fact that, first of all, this is now negative, 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 negative. Okay, the charge in the middle is obviously negative, but I can't really see it here. Okay, these lines are no longer pointing out. They need to all point back in again. Okay, let's delete, 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 delete. And this guy, I'm going to replace it with a minus sign because it's a negative charge. Okay. And now we can start to place them back again. And there we are. This is our electric field vectors all pointing into the center. Maybe our object manager, let's, there, I can certainly see the negative charge of the stuff now. Without being able to see stuff. Okay, so there would be our negative charge distribution. Okay, let's move back to our worksheet and see what's the next one we want to work on. Let's, okay, I'm going to close this. Just clear it. From my worksheet, I think the next one we want to work on is a dipole. In other words, I want you to try to draw the distribution for this guy plus this guy. Okay? Let's use the same method as we have just done now, but we will continue with this one. I'm going to give you some time to do it, then we'll take it up together.